and I'll make Nikolai the host. Cool. Okay, yeah, I can't see the breakout rooms anymore. So Nikolai has the power for that. Okay. So which problems do you want to do? Like, I don't have a poll set up, and also I lost the poll ability. Yesterday, like people were talking about like there was like this week's all like binary and like IEE, that kind of thing. What single precision numbers, how they work. Have people taken a look at this and like, do they know what is tricky and what they want solutions to?
I had a question.
Yes.
It was like about the one that, what's it called? I guess the professor showed. Do we have to do it the way he showed it, or can we use like the bin to deci and that?
There was a post in Piazza that confirms when the instructors said it was okay. You can use deck to bin. You can use bin to deck. I used that, and like I was able to do it in like just a few lines.
Yeah,
So,
because I saw what he did and I was lost. Thanks.
yeah, no need to reinvent the wheel. If the wheel exists, use it. Put it on your truck. Let's see.
Is that possible? You go over the last question, the structure stall, I think.
Which one? Lab 3, lab 5?
Lab 5.
Lab 5. So you want to go over maybe the last question?
Yes.
Okay, so there's a vote for question 5. Sorry we can't do this like as an official poll. Let's see.
Can we go over question 5 in lecture?
Let's see if they.
Yeah, he kind of like gave us the code pretty much and then sort of explained it.
Oh, okay. Well, hopefully someone screenshotted that. Well, was it in the recorded lecture, or did he like stop it and then be like, okay, here's the code for?
I don't
was in the
remember.
recorded.
I think he kept it going. Yeah, he
Okay,
was like
that's
talking
good.
about keeping it going or something.
As it should be. So 1 and 5 are given then.
The 5, I don't think there's a code. I just talk about it.
Okay. Well, let's see. Someone in the wants to go in the breakout rooms. I think Nikolai can handle that. So I think what we'll do is we'll go over like either 2, 3, or 4, and then we'll see what happens regarding. I think if we show a solution today that like the professor later shows on Wednesday, I think it's fair game to kind of just not count that towards like the 50% that we show. Oh, we did give the code. Okay, well, let's just do 2, 3, and 4 today, and then we'll just kind of blaze through and see how far we get.
Yeah, I think he showed my complement game and the sorting struct problem. So I think he did 1 and 5.
Mm-hmm. Yeah. Okay. So on 1, you can do it the way he showed, or we can use the my bin to deck. If you can figure out how to do that, it's very short. Like I think, don't compare yourself to like what I did, but like I was able to do it in like 3 lines. It's literally just like convert to binary, do the complement, like calculate the complement, then convert that complement back into decimal. You could do that. Just one word about bin to deck and deck to bin. Make sure that the input's a string, not a number. That's how they work. Look at the documentation for those if you're not sure how they like what inputs and outputs they give. And yeah, 50% of labs every week. It's more like 60% for this one, but maybe we will round up like 3 out of 5, just because there's only 5 questions this week. Anything else we need to cover? If not, we'll just get straight into 2, 3, and 4. Oh wait, Nikolai, did Kaya still want to be taken to the breakout room? I think he said in the chat.
I do. I missed that. Yeah, we'll go right now. Sorry.
Wait, Kaya, did you Kaya, did you like have your question answered?
No, I'll still go into the breakout room.
Okay, yeah, okay. Have fun, you too. And in the meantime, I'm going to. I should have this open actually. Let's see, E7. This is lab 5. Give me a second to open it up and be like, well, 15 seconds more. Extract all. Okay. So number 2 was, there's like 2 parts to that one. There was like the binary, and then there was the single to decimal, I believe. Let me just check to make sure. Floating point numbers. Oh no, they're my compare floats and then my single to decimal. The binary tree was number 4. Yeah. Okay, we'll just go in order. Floating point numbers. Here's what I'll do. I'm going to just look at the PDF shortly, and then so I'm going to show that. Can write some notes, pseudocode a little bit, and then we'll head over to the solution. Just so that, let's see, don't need to show computer sound. I'll just do that. Okay, let me know if you guys can't see, but I think this worked last time. Okay, so we're comparing 2 floating point numbers, which it's kind of the programming equivalent of decimals. So the idea is we have 2 numbers that are very similar to each other. Now, if you're still wondering what the point of this is, it's like if you're trying to find the tolerance within which like 2 very similar numbers are the same. Here's an interesting thing, right? I'll do this in MATLAB to kind of show you later on if I have time. But if you do like 25 plus like 10 to the power of negative 15 and 25 minus 10 to the power of negative, this is a negative sign, negative 15. And then you like, let's say this is A, this is B. If you do A equals B, this is going to be true. It's kind of a resolution sort of thing where MATLAB cannot tell the difference between 2 numbers if they're like almost identical. And you're trying to figure out in this problem what's tolerance, like the tolerance is going to be in this case like around 10 to the negative 15, something ridiculously small. And then you're trying to find that and be able to just tell given those 2 very similar numbers as inputs, like 2.99999, 3.0000000, etc., and be able to see like what's the tolerance for like within which those are the same thing. Let me see if I missed any details. I'll scroll down a little bit. So yeah, there's a line, by the way, in the solutions that like you print out the 2 inputs as like out to like 25 decimal places. I'll just kind of explain what this means. Float, F for float. Before we had D for double and S for string, kind of like that. Decimal points, 25. It's 25 decimal points. You could change that to 19 to 6 to probably not a million, but that's the number of decimal points you'll print out. So this is just going to use like the same syntax as like sprintf, this kind of thing that we are familiar with by now. If anyone has any questions on like the intuition behind floating point numbers, like there's some good videos on it. Look up like I think the computer file video, like that's computer PHILE on YouTube. Like they have it's just 10 minutes long. They have a British accent, pretty watchable. Okay, but if otherwise, like we can just go straight into the solutions if no one has any questions on this. It's pretty straightforward in what it's trying to do. The coding might be a little bit more involved, but like we'll see that. I'll kind of like do the countdown for clearing this. 5, 4, 3, 2, 1. Whoops. There we go. All right, let's stop share and let's go over to the MATLAB. I don't have the MATLAB open. Hold on. This is compare floats. Okay. This is the first part, by the way. So we'll get to the second part after this. Oh, sweet. I already have like the other ones already open. Okay, my compare floats. Share MATLAB. Where is it? MATLAB academic use. Solid. All right, let me know if some people can't see, but here should be right here. Here's the line I was talking about. Comparison is a cell array with these brackets on the ends, and it'll compare. It'll create a cell array with like 2 point dot 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 3 dot 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 dot. There's a bunch of 9s, a bunch of 0s. Cell array. And that's going to be the formatting of comparison. We're just initializing what comparison is for now. So that was comparison. That's the first output. We're already halfway there. So if x equals y, so if they're exactly the same, then we'll turn tolerance to 0. Otherwise, we're going to do all this business. So here, let me just break down what this is doing. So first of all, find the difference between this. Maybe this is like 10 to the power of -15. Say abs floor log 10 diff. So you're trying to find the order of magnitude. I'm going to use something different here. Let's do 15.1 for this. Let's say it's like a decimal for this. -15.1 is the exponent. So we're going to do log 10 of 10 to the power of -15.1. That's going to be -15.1. That's okay. That's kind of the order, but it has a decimal point attached to it. So let's try and round this down. Floor means round down. Round down. Ceiling is round up, by the way. It means round towards negative infinity. It doesn't mean towards 0, towards negative infinity. So it changes for like positive versus negative numbers. So rounding down, it's -16. Absolute value, okay, we'll change this to a 16. Let's do abs floor. Seems like an exercise video. And then n becomes 16. That's the order of whatever this is, like 10 to the -15.1. And then once we're done, we're going to take it over here to tolerance, 10 to the power of negative, whatever the tolerance is, -1. So like we're going to have the tolerance like a little bit bigger than what our difference is. Now notice this, the difference between difference. So 10 to the power of -15, this is always going to be true. 10 to the power of -15.1 is always going to be less than whatever this is, the tolerance, 10 to the power of -15. Did I do that right? Yeah. So tall greater than diff. Yeah, 10 to the -2 is 0.01, which is greater than 0.001, which is 10 to the -3. Okay, that works. And then it spits back tolerance back to here. Okay.
I had a question.
Yes.
So, wait. So you said you used floor to make it to like the -16 or whatever, right? And then
Yeah, round down.
And then you did that -1. Is that what you did, or what was it?
Yeah, 16 -1 from this line right here. Tolerance.
Wait, but like, could you just use seal to get you that, or is it like, because wouldn't it give you -15 if you use seal? So then you don't have to do that.
Let's see, seal. So then that would make it -15. I guess you could. I didn't write this code. If that works, it works.
Okay, thanks.
Actually, wait, that might not work if this is like, let's say we have -15. And then, so like, -15 is our difference. No, 10 to the -15 is our difference. So let's say this were like not -15. Then floor would give us 15, and this would be 15, and this would be 15. So we would still need to subtract 1 from that, so like 14. Your suggestion would work unless we have a whole number. if we have a whole number, we're going to look, oh, we don't want it to, our tolerance. This is a less than, or this is less than, not a less than or equal to. So if we have a whole number, we want to have like the next integer above that. So that's what this,
Oh,
what this
okay.
does. Yeah. Okay. Any further questions about this, or can I something in the chat? Approach the specific problem, how we can choose the appropriate functions. Yeah, I think the question's referring to the like stuff like log 10, floor, abs. I'm not sure. I didn't take a good look at the PDF. Like maybe some of those are under tips or something, but I guess just use these. If you don't have, yeah, I'm not sure how you do it without like log 10. So don't use log, by the way. Log is like base E default in MATLAB. I guess just remember these, the functions here, abs, floor, log 10. It's only those three. It's not too many new functions, I guess. Heard some people in the students were talking about like making a Google Doc or something with like a bunch of useful functions. So I'm not sure how that's proceeding. Okay, I'm going to clear in 5, 4, 3, 2, 1. Let's move over to the second part of 2. Yeah, Google and then mathworks.com has all like the documentations. Or like if you are looking for, oh, I don't know what it's called, but I want to know what it does, then. Okay, my signal to decimal. Let's see. This is, wait a minute. This is the second part, right? Let me just verify that. Floating point numbers, binary representation of floating point numbers. Okay. So this is in the PDF, by the way. It basically pseudocodes it out for you. There's like 5 cases. Like I think the most general case I can write here. And don't be scared by this, by the way. It's just a system for storing binary numbers in a way that's kind of fast for a computer to run. So like it's constructed for like efficiency, not for like, you know, it seems complex, but there's a reason for everything. 1 to the power of s, 2 to the power of e minus d. Let me fix that e, that's bothering me. E minus d times 1 plus f. And there's like 4 other cases, but like this is the main one. So like main case. Okay, what does this whole thing mean? So S, E, D, and F. And you'll see these like kind of laid out over here. There's like 3 parts to this. There's the parameters, there's like converting this would double. Oh wait, I see some stuff in the chat. Oh yeah, the sheet. So what does each of these mean? So sine exponent. This is, I know it's one way to call it is bias. I'm not sure if there's something that starts with a D. And this is fraction. So if you want more intuition on this, there's another useful tool to kind of do this. I kind of posted this in lecture once, where like it's called Float Toy. This is one useful one. There's a lot of useful ones out there, but this is the one I found. Just Google Float Toy, Google, and just play around with that. It has like different boxes that you can like click on and interact with. Here's like the S region. Here's like the E minus D region. Here's the F region, and you can like play around. Oh, this is a 0. This is a 1. This is a 0. And what kind of number does that produce? Just a fun little thing. But I'll kind of sum up what it's doing here. So there's like the first box. There's like a bunch of like 9 boxes. 8 boxes actually. 9 minus 2, and then add 1, and then there's the rest. So there's like 8, 1, and then like I can't subtract. It's 9 o'clock in the morning. this is a sign. If this first one's a 1, this is going to be a binary number, by the way, all of these. So if this is a 1, -1 to the power of s is going to be -1. So then -1 to the power of 1. So okay, this first one's going to be -1. If we change this to a 0, it's going to be 0. Anything to the power of 0 is just going to be +1. That's how we make sure it's positive or negative. Okay, what about this one? Let's say we have a bunch of zeros, and like the first one is, oh wait, there's another 0 over here, 1. What does this mean? This is how we calculate E. E equals 2 to the power of, and each of these is like a power, right? I'm gonna write 0, 1, 2, 3, 4, ... What does this mean? Well, okay, I have a 1 below 0, so I'm gonna do E equals 2 to the power of 0. Let's say I put a 1 here. Okay, we'll add on 2 to the power of 0 plus 2 to the power of 1. Okay, now bear with me. Here's what we're going to do. I'm going to take this, and I'm going to feed it into 2 to the power of E. Right now, it's going to be like 1 plus 2, which is 3, minus D, which is the bias. Now, in all examples I've seen, bias is 127. So this is still a very small number. It's like 2 negative 124. But like if you add on more of these, this becomes more and more positive. You have 2 to the power of 2 plus 2 to the power of 3, 2 to the power of 4, and it kind of starts defeating this negative 127 term over here. That's what that does. And then, oh, someone in the chat. Yeah, fraction also called the mantissa. Some jargon. So that's it for the E, and there's different rules for this. I mean, you see over here, there's like a bunch of like if-else statements. What I'm coding here is just the first case. The rest is just like you writing out the different cases, and it's just spelled out explicitly. If you can copy an equation into MATLAB, that's basically what this is. In my opinion, this isn't too involved in terms of like the cognitive coding part of it. It's just, oh, this is what S, E, D, and F are trying to do. Here's that 127 I was talking about. Here's just converting here's the binary string to num. This is useful, string to num. Convert a string into a number, or double, as we call it. Num to string, that's just reversing the process. And then we'll create a number bin that contains all of those numbers, because we started out with like a binary string. Okay, we'll go over to the mantissa or fraction. 1 plus f. So here's how this works. -1, we're going to continue the number line. -2, ... I don't want to write those out. It'll hurt my wrists. Let's see. I'm going to put 1 and 1 for now. Let's kind of subdivide these. Here's an f. And that's going to be equal to something similar, actually. It's 2 to the power of -1 plus 2 to the power of -2. And we could add more if we want. We're going to take that and we're going to add that to 1 plus f. And that equals 1 plus, I'm running out of room, but that's okay. 1 plus a half plus a fourth. 1 plus f will never be greater than 2. It'll just be like 1 plus some fraction. 1 plus 1/2 plus a fourth is 1.75. So if that's going to be like 2 to the power of 3 minus 127. We'll multiply all these together. Sine times this 2 to the power of whatever. You can see that in the line over here. Here's the sine term. Here's the ED term. Here's the 1 plus f term laid out. I'd scroll down, but there's nothing else below this. It's just 2 end statements. Close the function, close the if-else tree. I'll just like end, and there's another end below that. Okay. I'll take any questions for a few seconds, and then if not, 5 seconds, I'll clear it.
Can you just scroll really quick?
Don't believe me? Okay. Let's see. Annotate end. close the function, close the if else tree. Yeah, it looks long, but a lot of it's just the if else tree. All right. I think I'll just clear this then. 5 seconds to take screenshots, and then I'll annotate clear.
I had a question, but more for like the last one we did.
Sure.
Like for the two values, like the x and the y, do we always assume them to be like very close to each other? And like, because if they gave us one that was like a positive and a negative, if we subtracted one from the other, wouldn't that just like either increase the negative or like, I guess, add more to the positive when we
Yeah.
calculate the difference?
So it's that wouldn't matter because we're doing the absolute value. So it's like, is that what you're asking? Like if you have like, wait a minute. Yeah, rephrase your question actually. So if you have like 3 minus like -3. Oh, did I freeze?
You should be good.
Okay. Phew. So I can't hear what Alexander is saying right now.
Oh, my bad. Yeah, I like that. Yeah. So if you had something like that, yeah.
Yeah. 3 minus -3, -3 minus 3, 6, -6. In the eyes of the absolute value, these are both equal. They're equal distance from 0.
Okay, I see. So we don't have to like worry too much about that. Okay, yeah. Because I was just worried about like the difference and everything. But no, I see what you're saying. Yeah, that makes sense.
Cool. All right. That's that for that. I'll annotate clear. Okay. Single decimal. We covered all this. Didn't miss anything down here. Nope. This is all in the PDF, this stuff over here. Don't think I need to discuss too much about that. Let's do 4 first, just because I have that up. Binary tree. Okay, before we get into like the actual coding of this, I want to kind of illustrate what in the world is going on with this. First of all, let's start down here actually. We're going to do something where we find the median, because you're not allowed to use the median function apparently in this PDF. I'm not sure if the actual logarithm catches that though, because anyway, we'll have a subfunction that takes the median of an array and returns the median and where it is. We have, I mean, now I'll explain this later, but that's all this does. It's a very complex looking function that takes the median of an array. So we're going to do a few things here. First of all, A1, just take the array. Z, the length of the array. And A2, we're going to initialize this, but this is eventually going to be, I believe, a sorted version of the original array. Let's take a, if we have a complex looking function, let's just plug in a sample input. Let's do this 5, 1, 3. No, 5, 4, 3. Let's do. No, wait. 5, 3, 4. Let's make this as random as possible. 5, 3, 4. Sorry, let me make this a 6 just to make sure that, if we have like 1, 2, 3, like the indices, we don't interfere with those. Okay. J1 to Z. So this is going to be 1 to 3 because we have a length 3 array. AB, maximum array. So this works differently, similarly to actually how our function's going to work. It's the maximum and the index. That's the syntax. So this is going to be, we're going to run this several times, but the first loop, I'm going to take that up here actually. It's going to be 6, and then where's the 6? It's going to be 2. And then this next line over here, array B, is going to nix out that 6. Can nix the 6. So it's going to be 5, 4. It's going to be the new one. So this is going to be A1, right? Array B, no, wait, array, sorry. That's just gonna be this. The reason why we make the A1 is because we want to create a version of array that we're not modifying. 5, 4 array, and then we're gonna assign A2J, so that's gonna be A21 first, and that's gonna be A, which is 6. So this is array now, and this is going to be A2. A2. I'm just drawing this out just to make sure that you guys know how this thing works, because here's 6. We'll repeat the process. This will be 4, and this will be 6, 5. You'll see the pattern is this will always make like a reverse sorted array. 6, 5, 4, and then the array just kind of disappears. It vanishes. This is the final A2. It's a sorted version of the original array. That's all this is. This is A2 equals sorted. You can rename it to like a sorted array if you want, more descriptive. Okay, that's the first part. What are we doing down here? Well, we have z plus 1 over 2. So that's going to be like the middle position of whatever that array is. We have a 3-element array. So this is 3 plus 1. This is 2. Okay. This over here, this is easier to see if we have like a 4-element array, but like, so like if we have 4-element array, we have 2.5. So like 3 becomes 2, 4 becomes 2.5. Let's imagine we had 2.5 for the time being. MD, the minimum of, there's a lot, this is ceiling and the floor again. Ceiling of T, so this is just like A2, 2 and A2, 3. This is what you see with like median of like even numbered, if we have like 5, 6, 7, 8, you'll take like the median as like the average of these two. Okay, but in this case, we're actually not going to do that because we actually need to find the kind of like the lower. We're going to do things a little bit differently. We're just going to take the lower of the two numbers. A little bit different, but it's necessary for this type of problem. We're kind of constructing a tree. MD, and then we'll return the index, the location of that median. I mean, this right here, I mean, this is already the median. We're taking this as a median, MD, and then we're locating that, and we're doing that as index. And the reason we have find, that's just if we have multiple 6s. That's all it is. First instance. Okay. And remember, A1's the initial array. So we pull it out, and then, okay, I'm going to clear this in a few seconds. So 5, 4, 3, 2, 1. All of that ado to find the median. You'll know why this is a built-in function. Find median. Okay, we'll go back up and then we'll see what kind of funny business we're up to up here. Unfortunately, we can't fit all of it in one, but I'll scroll down eventually. And let's see, how are we doing on time? We got an hour left. Okay. Once again, initializing one of our outputs. That's tree up here. And what this is going to look like is, and we'll kind of see that with these first kind of base cases of sorts. Spoiler alert, this is a recursion problem. So we'll start with, we have an array of 1. So this is case number 1. I'll number these. Case 1, we have one single number in our array. It's not really an array, it's just a number. 4. We'll do a tree that looks like this. Nan. I think this is like the my knight problem where you have your knight already at P1 equals P2. Remember, like P1 equals P2, that kind of thing. This is one of our base cases. Okay. Now, is empty array, if we don't have an array, then we're just going to have case 2 be nan. Our entire tree is nan. So depth is 0. This is a more complicated case than the one that is kind of more rewarding to look at. We're going to use my median. We're going to find the median of array. You can probably read this out and tell what it's trying to do. Array, the location of, so this here's where the location's important. Remember our array 5, 5, 6, 4. We found the median as, so I mean, this is going to be 5 in this case. So 5, we're going to nix this out. We're just going to turn this into 6, 4. That's what this one's doing right here. It's erasing the median. Because what it's going to do is it's going to pull out that median eventually. For now, we're going to create 2 vectors. Everything below 5, everything above 5. So in a bigger array, it's going to look something like this, like median, and then 2 arrays that are like roughly equally sized. Not exactly in all cases, but like it'll be like 1, 2, 3, 4, 5, 6, 7, 8, that kind of thing. Low vector and a high vector. And this is just them initializing it, and this is how they actually create the thing. Here's the sorting hat. If array k is less than or equal to the median, put it in this low vector. Otherwise, put it in the high vector. One of those two. Okay. Not too much else to go through. Something in the chat. Yeah. Okay. Clearing this in 5, 4, 3, 2. Now we can go over redrawing those if we need. Whoops. Here's the. I'll kind of. Whoops. Kind of re-show this as necessary. There we go. Fit as much of it as we can. 2 end statements. Where were we? We are here. Here is where the similarity between this and like the MyNight problem is. Because remember, we're drawing a tree. We're starting up here, and then we're kind of creating 2 children. And those children become parents, and they have 2 more children. And 2 more children. It becomes this branching tree. Recursion is kind of designed for these branching problems, where you make a function call, and then each of those makes a function call. And once you reach one of the base cases, this probably won't look like this. It'll maybe look something like this. Once you reach these base cases, you'll go back up the function, and you'll track how long it took you to get there. Let's say this one only took 2 branches to get there. This took 3 branches to get there. So here's what the recursion I was talking about it later. You're going to rerun this code with, we're going to take these 2 vectors that we split it up into. Here's the median, boop, 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 and rerun these. I'm going to take the median out of this one. Median, let's see, low, median, high, like that. And then we're going to keep going. And so this is after the recursion, right? Here's the recursion. And then after we're done with all this, we're going to create our tree. That's just like MD, and then the 2 medians. This A right here, this B, that's just the median of whatever this child array is spitting out. And here's the depth counter. It's like the move counter for MyNight. It's how many times this will step 1. It'll go 1, 2, 3, 4. It basically counts the number of times it takes from the leaf all the way up to the stem or the trunk of the tree. And then, now this is a little bit different than the night problem. You're going to pick the maximum depth. So, 3, it's a maximum of 3 depth. So that's how big the tree is. And that's all it is for this problem. Clearing in 5, 4, 3, 2, 1. Any questions so far? Log time. Yeah. Wait, is it possible for a sorting array to have like a, what's it called? To do it in log time? Because I thought the fastest you could do for a sorting algorithm was like ON time.
No, this is just search, and then insertions and removals are also log n time.
Okay.
But if we take any array and try to sort it, it would be n log n on average.
Gotcha. Okay. We covered 2. We covered part 2 of 2, and then we covered 4. Let's move on to 3, and then we'll do any like miscellaneous questions after that. Now, let's see what 3 is. Give me about 15 seconds. Ith largest element. Interesting. So we're gonna go over to that one and then see what that business is all about. Ith element. Let's just take a brief look at what this is trying to do, because I haven't actually looked at this problem yet. Okay, so array is some unsorted array. I is what element do you want? So wait a minute. Ith largest. Oh, okay. That just specifies what largest element you want. And then it just returns the value and the index. So similar to the median and the max function I showed you in the last one, regarding you're trying to find something and the location of that thing. Let's see how we're going to try and do that. Initialize as always. Any. Length. And any again. So initializing array 0, initializing sorted. So how are we going to do this? I think the main thing with this is just sorting it. I mean, it's not really, the main code isn't finding like the ith element. It's just make a sorted array, and after that, it's like super easy. This is literally just one line, like this index part. Find where it is.
Yeah, so the main strategy is to sort the array, find the value of the ith largest element, which in a sorted array would be either nth minus I if it's sorted in ascending order, or just I if it's descending, and then finding the index of that value in the original array using the find function with the appropriate argument first. And we use first because the array might have duplicates of that value, and we only want the first occurrence.
To answer the chat, it takes like between like half an hour maybe for this to compile, and then I'll upload it. I'll upload it by probably by noon today. Depending on, it's like the limiting factor is like the size of the video, so it just takes a while to upload. So it'll be uploaded to the same place though. Oh, where? Oh, actually, usually I upload these to my YouTube. So I recently created like a playlist for that. I can link it in the chat for people who need it. But no, I'll do that after this actually. Once I have all these things out of the way. Wait a minute, how do we get back? Yeah, actually, Nikolai, do you have access to that, or did I ever? I think I sent it out in like a B courses.
Yeah, you did. You sent an announcement.
Can you post one of you in a? Can one of you guys post in the chat? I think don't have it up right now. I'll get back to the problem, and then I can talk more about that if you guys want. It's just like I have 2 playlists. One for, I think you just do like the Tuesday, Thursday one. I have another one that I also upload onto there. This is very, by the way, this chunk of code right here is very similar to what we did for my binary tree. If I can go back to that temporarily. No, not by my binary tree. Where was it? My median part. This right here, it just sorts the array that we want. So here we have like sorted is, it's just going to take, oh, here's like a jumble of numbers, 1, 7, 2, 3. So step 1, find the max. That's 7. My max equals what? That's not a question mark. Max equals what? And then put max in sorted. So that's going to be 7 is the first one. And then 3, loop until sorted is filled. That's all this does. And then everything down here is just using the fact that this is sorted and being all, yeah. No, thanks, Eliana. Okay, ith element was easier than I expected. Shorter, at least. Initialize, sort. Initialize, sort, and then find. That's all that does. If I'm missing anything, or if there are people who have questions, say them now or hold your peace. Okay, I'll clear these in 5, 4, 3. Okay. This is all going to be uploaded, so if you want to review any part of it, you can save the playlist. Also check the email I sent out. Hopefully everyone's on that list. I know some people might be coming from other labs, question mark? It's in the chat, the link. So it's 10:13. We've made pretty good time. So I think, okay, I'm gonna stop the recording here just so that it won't be too long.